Just about time. Okay. Question. I had a question for you guys. What was my question? Oh yeah. I don't know how to say his last name. Is it Yeon, the instructor for one of the instructors for Math 21A? Does anyone have him for their class? Okay. I was gonna ask if he was assigning any homework because it didn't look like it, but I guess that's not a concern for all because the other teacher certainly is assigning homework, right? Like on web work? Cool. Good. Uh-huh. That's an interesting choice as an instructor.
He's telling me I'm scared because the midterm, he doesn't know what to study for.
Right. It makes it challenging to learn the stuff if there isn't any homework to do. So you might actually refer your friend to Dr. Kuba's website that's on our code classes website because there's lots of homework problems there with the sections and with the material. So that's probably a good resource for the students who are in the class that doesn't have any homework. So you can't even begin to imagine. Because that's how you're gonna actually learn this stuff is like doing it at home, right? You can watch me do math all day long, and that might help a little bit, but like really, you're going to learn it by doing the homework or whatever work you're going to do. Let's see, Co-21A. Today is the 13th. I feel like we should talk about limits. Limits seems like where everyone's mostly at, so let's talk about limits today. Let me look at one real quick thing here. Sure, yeah, that's fine. Where'd you go? Sure, yeah, okay, yes. And we'll start kind of just with the very basic idea of kind of what a limit is or how you might think about a limit. So let's look at some examples with some pictures. Here's a function, a piecewise function, f of x equal to x squared when x is less than 2 and x plus 2 when x is greater than 2. If we graph it, it looks something like this. It's the usual parabola to the left of x equal 2. When I say usual, I mean like the one where the intercept or the vertex is the origin. So it looks vaguely like this. It comes up to the point 2 comma 4. And then the line or the other piece of the piecewise graph, y equals x plus 2 is the straight line that goes to the point 2 comma 4. It doesn't actually include it, looking like that. Again, vaguely. And I'll point out here that, oh, I'm looking at the wrong thing. That's fine. It's still a good example. I'll point out that for this example here, the limit as x approaches 2 of f of x, well, we can think of this as kind of two pieces. There's the left piece and the right piece. So we can see that the limit as x approaches 2 from the left, well, if we're left of 2 or less than 2, by the way, I like the fact that left and less both start with L. That helps me remember which is which. So if we're left or less than 2, the function we're using is x squared. And then typically, when you're trying to evaluate a limit, the easiest way to try to first go about doing so is just to plug in whatever value x is approaching. So we're going to substitute in x equal to 2. We're going to get 2 squared, which is 4. On the right-hand side, the limit as x approaches 2 from the right of our function. Well, on the right-hand side of 2, the function is x plus 2. And again, if we substitute in 2 for x, we're going to get 2 plus 2, which is 4. So here's what we're really saying with this notation. When we see that the limit as x approaches 2 from the left of x squared is equal to 4, all this means is that as x gets closer and closer and closer to 2, the function values get closer and closer and closer to 4. They don't necessarily have to ever equal 4. We just are saying the limit is 4. We do say that the limit is equal to 4, even though the function doesn't actually equal 4 here, right? This function isn't defined at that point right there. But since the left-hand limit and the right-hand limit have the same value, we can say that the limit as x approaches 2 of f of x is 4. Note, or just as a point of interest here, f of 2 is undefined, right? This function is not defined at 2. The limit has nothing to do with what's happening at x equal to 2. X equal to 2 could be literally anything, and the limit is still asking what's happening as x gets closer and closer and closer and closer to 2. What's happening to the function? Oh, the function is getting really close to 4. Great. We can answer that question. I will point out, just because eventually we'll move there, this function would not be continuous at 2 because although the limit exists, the function doesn't exist itself at 2. But again, we're not quite to continuity yet. Let's look at another piecewise example that has a little bit more going on here. So let's say we have, sure, sorry, let me try to stay in frame. Let me do one thing real quick. I always make this mistake of trying to do that. Yes, question. I did not pass it around yet. Give me a minute. I'll do that in a 6. Yeah. So let's go ahead and look at this next function. Let me see if I can remember to number my examples here. So number 2, we have that g of x is equal to the following piecewise function. It's got 3 pieces. It's x squared plus 1 when x is less than or equal to 0. It's x plus 1 when x is bigger than 0 and less than 3. And it's equal to the square root of x plus 1 when x is greater than or equal to 3. In fact, I'd like you all to try drawing this piecewise function before I draw it. And here's the attendance form coming around. And if your name's not on there, just write it at the bottom. If your name's not on there and you'd like to be added to the canvas, let me know and I'll add you to the canvas. Like this under here. All right, let's see. So x squared plus 1, typical parabola shape, but shifted up 1. So it's going to look like, let's draw it in black. It's this piece of your typical parabola shifted up 1. And then for the middle piece, when x is between 0 and 3 and y is equal to x plus 1, so it's a straight line. I know that if I could plug in 0, I would get 1. So I would actually get this point that's already there. If I could plug in 3, I would get 3 plus 1, which is 4. So over at 3, I get a y value of almost 4. So there's the next piece of my piecewise function. And then for the last piece, the square root of x plus 1 has your usual square root shape, shifted 1 to the left. But then we're not starting until we get to x equal to 3. So even though the square root of x plus 1 would look something like this, where it's got the point -1, 0, and 0, 1, and 3, comma 2, we're not going to start it until we get to the point 3, comma 2. So over here at 3, we've got 3, comma 2. And it looks something like that. Cool. Let's ask some questions about limits. Specifically, let's ask about what's happening at 0 first. So part A here, what's the limit as x approaches 0 from the left-hand side of f of x? G of x, apologies, g of x. So again, with limits, graphs are great. You can totally see on this graph that as x is getting closer and closer to 0 from the left-hand side, the function values are getting closer and closer and closer to a value of 1. Or you could just use the piece of the function that g of x is when x is less than 0. That's this piece here. And then you can substitute in 0 and get 0 squared plus 1, which is 1. Similarly, if we take the limit as x approaches 0 from the right-hand side of g of x, that means we're approaching now 0 from the right. And we can see that the y values or the function values are also getting closer to 1. We could also see this by just using the right piece of the function. If x is bigger than 0, now technically, if you're saying x is bigger than 0, technically it could be this piece or this piece, the second or the third piece, but it should be the middle piece because it has to be getting close to 0, right? This piece isn't starting until x is bigger than or equal to 3. It's not the lost piece, it's this middle piece. So its limit as x goes to 0 from the right of x plus 1, and we get 0 plus 1, which is 1. And since the left-hand limit and the right-hand limit have the same value, the two-sided limit exists and is equal to that value. So these two pieces together mean that the limit as x approaches 0 of g of x is equal to 1. Because the limit as x approaches 0 from the left of g of x is equal to the limit as x approaches 0 from the right of g of x is equal to the value that we got, which is 1. So for a limit to exist, the left-hand side and the right-hand side must exist and equal the same number. If they don't, the limit does not exist. Or I should say the two-sided limit does not exist. In fact, we can see that for what's happening at 3 here. If we look at 3, the limit as x approaches 3 from the right of g of x. Well, again, you can either see it here that as we approach 3 from the right-hand side, the x values are getting closer and closer to, the y values are getting closer and closer to 2. Or again, you can use the correct piece and say it's the square root of x plus 1, and as x approaches 3, x plus 1 approaches 4, and the square root of 4 approaches 2. On the other side, if we approach 3 from the left-hand side, which I know I'm getting kind of messier with my arrows, the y values are getting closer and closer to 4. And we can see that if we plug it in as well. The limit as x approaches 3 from the left of g of x is equal to the limit as x approaches 3 from the left of the piece where we're just less than 3, so the x plus 1 piece. And if we plug in the 3 for x here, we get 3 plus 1, which is 4. These are not a match, so the overall two-sided limit doesn't exist. The limit as x approaches 3 of g of x does not exist. We have a jump discontinuity here. And if I can explain something or zoom in a little bit for people, I'm happy to do so. I recognize sometimes my writing is too small and I can try to make it bigger. But really genuinely, if you have a question or a clarification of something I've written, don't hesitate to ask. I'm happy to explain anything I've written. Questions about any of this so far? So I would say very generically, when we're looking at limits, we're just asking a question. We're asking what y value is this function getting closer and closer to as x is getting closer and closer to this particular point, with this particular value, or potentially going off to infinity or negative infinity if that's what we're looking at, but not quite yet. I want to say this the right way. Graphically, you can do this kind of thing, but a lot of times we don't want to draw the graph for limits. So we kind of pretty quickly jump to saying, yeah, we can evaluate limits by just substituting in the value that x is approaching. For example, I'm still using numbers. I'm still using numbers. Great, good job. I could ask, what's the limit as x approaches 2 of x squared minus 4x minus 3? Oops, you can't see that. Sorry. And not seeing any pitfalls here, I'm just going to plug in 2 for x and get 2 squared minus 4 times 2 minus 3, which is what, -7? I know what I want to stress. I want to stress that the limit doesn't actually care about what's happening at the point. It cares about what's happening near the point. And that matter becomes more and more important when we start looking at examples like the following. The limit as x approaches, sure, 8 of x squared minus 5x minus 24 over x squared minus 64. Here, if we try plugging in 8, something else is going to happen. We're not just going to get a number. We're going to get, let's see, 64 minus 40 minus 24 over 64 minus 64. We get 0 divided by 0. Great. And 0 divided by 0 can be anything. So I want to make this absolutely clear. 0 over 0 is what's called an indeterminate form. There are many more of these that we'll encounter later on, like in chapter 4, when we talk about L'Hopital's rule. But for now, 0 over 0, and we'll see later on, infinity over infinity are the two types of indeterminate forms that we're going to encounter. And what that, oh, actually, we'll encounter a couple more other ones too. Yeah, there's other ones coming up too. And what that means is, well, there's two meanings. What it means is it can be anything. You can literally get any value from a 0 over 0. What it means for us, as far as our approach is concerned, is that we have to do some algebra typically, or some sort of manipulation to try to see what this actually is, because this particular limit is going to be, I don't know, like I think 11 over 16. But let's find out. So here's the idea. For this limit here, we're going to rewrite it as the limit as x approaches 8 of the top factors as x minus 8 times x plus 3. The denominator factors as x minus 8 times x plus 8. And here's the thing we have to remember that's true. This limit is asking the question as x gets really, really, really close to, but not equal to 8, what value is this expression approaching? Well, as long as x isn't 8, which it's not, because it's like 8.00000001 or 7.9999999, but whatever you plug in that's not 8 right here, not 8 minus 8 divided by not 8 minus 8 is going to be 1. Right? Those things cancel because they're both specifically not 0. I know I'm really kind of hammering this point because it's important, right? We are not plugging in 8 yet. X isn't actually equal to 8. It's just getting close to it. And as long as it's not 8, which it isn't, these things get to cancel, which is why we're allowed to do this algebraic manipulation. Because we're like, oh yeah, not really 8 yet, or ever actually. We're just saying if x was getting close to 8. Well, cool. If x is close to 8, x minus 8 divided by x minus 8 is like 0.01 divided by 0.01, which is 1, or whatever it is. But then you can say, well, now its the limit as x goes to 8 of x plus 3 divided by x plus 8. Or, in many more words, what value is this getting close to as x gets close to 8? Well, as x gets close to 8, the top gets close to 8 plus 3, and the denominator gets close to 8 plus 8. So we get close to 11 over 16. So here's what we're going to write mathematically. The limit as x, and you don't need to write this again, really. I'm writing it in again so I can make kind of a point. The limit as x goes to 8 of x squared minus 5x minus 24 divided by x squared minus 64 is equal to 11 over 16. That is the math we write. But the meaning is that this function gets close to 11 over 16 as x gets close to 8. That is the meaning behind this expression. This function probably never actually is equal to 11 over 16. That's okay. Not what we're talking about. So let's see. What else do I want to say here? Yeah. So I would say with these 0 over 0 types of limits, which are kind of the majority of the types of limits you encounter that aren't having to do with infinity, there's kind of three things that happen. One of the things, which we've encountered already, is where you factor. So for example, if I were to ask you all to try, say, numbers, do I remember numbers? Still, yep, number 5 here. The limit as x approaches 2 of 4x squared minus 3x minus 10 divided by 6x squared minus 12x. What's the first thing you're going to do? That's the second thing we're going to do. What's the first thing we're going to do? Plug it in, because it might not be 0 over 0. Maybe someone gave you something really easy. It's just going to work out nicely. So let's see. If we plug it in, we get 4 times 4 minus 3 times 2 minus 10 over 6 times 4 minus 12 times 2. No, it looks like it's 0 over 0 because I got 16 minus 6 minus 10 over 24 minus 24. Okay, here's a good piece of information. We saw that plugging in 2 gave us 0 over 0. That means if you have polynomials on the top and the bottom, x minus 2 has to be a factor. So factor this, and I want you all to do it, but you already know for sure on top x minus 2 is going to be a factor, and on the bottom x minus 2 is also going to be a factor. So find those other factors. The bottom one I've written kind of stupidly, right? Like the bottom one, the other factor, 6x. Here's what I'm thinking about the numerator. X times something has to give me 4x squared, so it better be a 4x. And negative 2 times something has to give me negative 10, so it better be a positive 5. And if you check the middle terms, it should work out. 5 times x and negative 2 times 4x gives me a 5x minus 8x, which is negative 3x. It's a really handy way of doing this. If you see that plugging in a number gives you a 0 for a polynomial, you know that x minus that number has to be a factor of that polynomial. It's actually the fundamental theorem of algebra. So kind of neat. So I wasn't really thinking about like, how do I multiply the negative 40 and out of the negative 3 and whatever the weird way of factoring a quadratic is. You just say, cool, I know x minus 2 has to be a factor. I have to have a 4x there to make 4x squared. I have to have a 5 there to make negative 10. And then the middle terms will work. It has to. You've got no other choice. And then we get to divide those and get 1. I like to write one more step here, even though you could just plug it in. We have the limit as x goes to 2 of 4x plus 5 divided by 6x. That's going to be 4 times 2 plus 5 over 6 times 2, which is 13 over 12. Neat. One more of these, well, similar to this. Let's try the following. The limit as x approaches negative 3 of 2x squared plus 5x minus 3 over x cubed plus 27. And certainly the bottom is going to be 0 because negative 3 to the third power is negative 27. Let's check what the top is. I hope it is. Otherwise, you have a whole other can of worms you have to deal with. Let's see. 2 times 9 is 18. Minus 15. Nope, that's 0 as well. So it's definitely a 0 over 0 type. So let's do the same sort of thing. The 0 over 0 type, so we know we have to be able to factor out what? Well, we plugged in negative 3 and got 0, so we should be able to factor out x plus 3, or minus 3 if you want to say it, but I would say plus 3. So on top, that's not too bad. You got x plus 3 times, let's see, it has to be a 2x, and it has to be a minus 1. And that works. So you get 2x squared, you get plus 6x minus x is plus 5x, and then minus 3. On the bottom, though, there's a little bit more going on here. So x cubed plus 27 is a sum of cubes. It does factor. And more generally, when you have a cubed plus b cubed, you can always factor that as a plus b times a squared minus ab plus b squared. So in this problem, we have x cubed plus 3 cubed, and it's going to factor as x plus 3 times x squared minus x times 3, or 3 times x, plus 3 squared. Totally works. It actually, one second. It actually works for a sum of cubes or a difference of cubes. For a cubed minus b cubed, it's going to be a minus b times a squared plus a times b plus b squared. Question? Yes, of course. Sorry, thank you. Yeah. Sorry. If I tell you to wait for that, just yell out to move it up. Apologies. Yeah, yeah. If you can't see something, be like, hey, James, you can't see. So, one thing about this is kind of so there's an acronym for this difference of cubes, sum of cubes things. It's called SOAP, where when you factor it, you get a plus if it's a plus, minus if it's a minus. So S for same, and then plus gives you have a minus sign here, so it's opposite. Minus sign here gives you a plus sign here, opposite. And then the last one is always positive. SOAP, SOAP. So that's how you factor a sum or a difference of cubes. Kind of neat. Anyway, the x plus 3's divide to 1. We're left with the limit as x approaches negative 3 of 2x minus 1 over x squared minus 3x plus 9. We plug in negative 3 and we get negative 6 minus 1 on top and 9 plus 9 plus 9 on the bottom, which is negative 7 over 27. So if you're lucky enough to have a 0 over 0 situation where it's just polynomials, things will usually factor. In fact, they kind of have to factor. But that's not the only 0 over 0 situation we might encounter. For example, we might have something like the limit as x approaches 5. Sure, we'll do this. Of 3 minus the square root of x plus 4 over 25 minus x squared. Well, that's a little crooked there. Okay. And again, you should always do, even if you're pretty convinced it's 0 over 0, just do a quick mental check. See, if I plug in 5 on top, square root of 9 is 3, 3 minus 3 is 0. Yep, okay, bottom, yeah, 25 minus, yeah, definitely 0 over 0. But good to check. Probably even good to write it down on an exam so that you know that you have to do something. So we have to do something. Because it could be anything. Sometimes it is 0, but I want to make it really clear. 0 divided by 0 is not generally equal to 0. It is really indeterminate. We don't know. And if you think about it, it kind of makes sense, right? 0 divided by 0. How many times does 0 go into 0? Take your pick. Anything will work. I'm going to pick 7. Let's see, 7 times 0 is 0. 0 minus 0. Yep, checks out. The remainder is 0. But you could have picked anything, right? I'm being a little bit silly here, but I really want to make it clear. 0 divided by 0 can literally have any value. It could even not exist. It could even be infinity or not, or negative infinity. Or it could be 5 or 17 or negative a billion. So here, when you've got radicals, we often want to multiply by the conjugate of that. So we're going to rewrite the limit as x approaches 5 of 3 minus the square root of x plus 4 over 25 minus x squared. I probably could factor that. Oh, well, I didn't. And then we're going to multiply by the conjugate of the radical part. So the conjugate of 3 minus the square root of x plus 4 is 3 plus the square root of x plus 4. It's just the same expression, except you've changed the middle sign from negative to positive or positive to negative. The whole point is that when you multiply these conjugates together, you're going to get a difference of squares, right? If you look at a minus b times its conjugate, a plus b, you end up getting a squared plus ab minus ba minus b squared, but the ab and the ba are opposites of each other, or I should say negative ba and ab add up to 0. And so you just get a squared minus b squared. So when you factor a difference of squares, it factors into conjugates. And when you multiply conjugates together, it multiplies to a difference of squares. So here, we're going to actually multiply out the conjugates, the two pieces on top, but not the pieces on the bottom. right? Multiplying 25 minus x squared by 3 plus square root of x plus 4 isn't helpful to actually multiply out. So what we should do on the bottom is just leave them as it is. In fact, we should factor the 25 minus x squared. So the 25 minus x squared is going to be 5 minus x times 5 plus x. Order does matter here. It is specifically not x minus 5 times x plus 5. If the 25 is first, the 5 has to be first. If the x squared is first, then the x is first. And then we have this other 3 plus the square root of x plus 4 piece. And on top, what we should do is we should skip the writing it all out. I shouldn't really write 9 plus 3 times this. I'm going to write it, but we shouldn't really write 3 squared plus 3 times the square root of x plus 4 minus the square root of x plus 4 times 3, which is 3 times the square root of x plus 4, minus the square root of x plus 4 times the square root of x plus 4. I am writing it out this way with two purposes in mind, though. So normally you would skip this step. You'd be like, cool, the middle terms add up to 0, and you end up with the limit as x approaches 5 of 3 squared, which is 9, minus the square root of x plus 4 squared, which is x plus 4. Now be careful here. That's wrong. Because it's 9 minus the entirety of the square root of x plus 4 squared, which is parentheses x plus 4. Here's a good check on that. At this point, we haven't canceled anything out. Meaning, if I were to plug in 5, I should still get the same 0 over 0 I started with. But if I didn't have those parentheses there, which are kind of hard to disappear now that I've written them there, but if you pretend for a minute that you didn't have the parentheses there, and you plugged in 5, you'd get 9 minus 5 plus 4, which is 4 plus 4, which is 8, which isn't 0, which is a problem. We should still be getting 0 when we plug in 5. So that's a good reminder that, oh yeah, we need that parentheses there because we still should have a 0 over 0 until we cancel something. Okay, it's a lot. So obviously, or maybe not obviously, but hopefully, obviously, I'm writing a lot more steps than you probably should be if you're doing this work on your own. Like you should write as many steps as you need, but like I feel like you probably jump from like the step right with the conjugate to the step down here. The middle step there is way more than I need. And simplifying the top, we get, let's see, 9 minus x plus 4 is going to be, let's see, 9 minus 4 is 5, and then minus x. Good. I have one of those in the denominator. It's a good sign. So then we cancel those. I really don't like the word cancel. It's just such a loaded word in math. I would like to say that those divide and leave behind a what? 1. Specifically in the numerator, because otherwise there wouldn't be anything in the numerator. So I have the limit as x approaches 5 of 1 over 5 plus x times 3 plus the square root of x plus 4. And now that I've finally eliminated the parts that were making it 0 over 0, we can plug in 5 and get 1 over 5 plus 5 times 3 plus the square root of 9, which is 3 plus 3, or 6. So we end up getting 1 over 60. Oops, sorry. Oh, yeah, interesting. So, oh, sorry. Square roots are usually where you see multiply by a conjugate come up, with one other addition. So just as an example that I won't do, but I would encourage you all to try on your own, if you had, say, something like the limit as x approaches 4 of the square root of 2x plus 1 minus 3 over 2x minus 8. This would also be a 0 over 0 type. And your first step would be to multiply by the conjugate, the square root of 2x plus 1 plus 3 over the same thing. And you can do that on your own at some point. But there is one other instance where multiplying by the conjugate is actually kind of a really good way to go. And it's when you have one of these four things. So if you have some limit, we'll say the limit as x approaches pi over 2 of 1 minus sine of x over cosine of x. Well, you might not be surprised to see that this is also going to be a 0 over 0 type, because sine of pi over 2 is 1 and cosine of pi over 2 is 0. So we get 1 minus 1 over 0, which is 0 over 0. And I'll say the following. When you see a 1 minus sine of x, or a 1 plus sine of x, or a 1 minus cosine of x, or a 1 plus cosine of x, multiplying by its conjugate is something that's worth trying. Why? Let's see. So if we rewrite this and say it's the limit as x approaches pi over 2, I know what I was going to say. When you're doing these problems, I would encourage you to get in the practice of writing the limit part every step of the way. Because on an exam, it's worth a point, at least. And also, probably more importantly, this thing has a different meaning if you don't write the limit. If you don't write the limit part, you're just saying, here's a function. Maybe it's got a graph or something. Whereas when you write the limit, you're saying, oh, there's a question to answer here. What is this function getting close to as x is getting close to pi over 2? So the limit is a really, really important part of what the whole meaning is of the thing we're writing. But I know it's annoying to write every time. So we've got 1 minus sine of x over cosine of x. We're going to multiply that by the conjugate of 1 minus sine, which is 1 plus sine, over the same thing, right? We're only allowed to multiply by 1, so you don't actually change anything. And I should point out, all my examples, the conjugate thing happens to have been in the numerator. That's not necessarily always the case, right? You could just as easily have had the 1 minus sine in the denominator and multiply both sides, the top and the bottom, still by 1 plus sine. So the thing you're multiplying by the conjugate of could be either in the numerator or the denominator. All my examples happen to have been the numerator. Terrible planning. So let's see what we get here. So 1 minus sine times 1 plus sine. We know we get the first thing squared, which is 1. We know the middle terms cancel out, the negative sine times 1 and the positive sine times 1. And then the last part is negative sine times positive sine, or as we usually say, it's minus the second part squared. So minus sine squared of x. And on the bottom, these things aren't conjugates, so we're not going to multiply them out. We're just going to write it as cosine x times 1 plus sine of x. Now, why might that be helpful? Well, because when you multiply 1 minus sine or 1 plus sine or 1 minus cosine or 1 plus cosine by its conjugate, you end up with a trigonometric identity. Specifically, the one that's coming from the fact that cosine squared of an angle plus sine squared of the same angle is always equal to 1. So we have 1 minus sine squared. If we subtract sine squared from both sides, we can see that cosine squared of theta is equal to 1 minus sine squared of theta. So when you get to a 1 minus sine squared, sorry, you can replace that with a cosine squared. So we can rewrite our limit as x approaches pi over 2 as the limit as x approaches pi over 2 of cosine squared of x divided by cosine of x times 1 plus sine of x. And now we can cancel one of the cosines, right? Cosine squared divided by cosine, you're left with a cosine on top and no cosines on the bottom. So now we're left with the limit as x approaches pi over 2 of cosine of x, not cosine squared of x, and on the bottom, just 1 plus sine of x. And now we can actually plug in pi over 2 and get cosine of pi over 2 divided by 1 plus sine of pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we get 0 divided by not 0, which is always 0. So those are kind of the two instances I think of where you want to multiply by a conjugate. You've got a square root plus or minus something, or something plus or minus a square root, or a 1 minus sine, or a 1 minus cosine, or a 1 plus sine, or a 1 plus cosine. Yeah. Okay. There's one more algebraic thing we talk about typically for dealing with limits, and it's the following. So the last kind of algebraic thing we usually see is something like if I had the limit as x approaches 3 of 15 over x minus 5 over x minus 3. And doing some quick mental math here, we see that, yep, 15 divided by 3 is 5, and 5 minus 5 is 0 on the top, and 3 minus 3 is 0 on the bottom. So once again, it's a 0 over 0 type of limit. Here, we typically get a common denominator. So, right, because we have fractions and fractions. So on top here, I'm going to take this 5 over 1 and multiply it by x over x. So that we have fractions in the numerator that we can actually subtract together. So you got the limit as x approaches 3 of 15 over x minus 5x over x. I'm just going to write as 15 minus 5x all over x divided by x minus 3. Okay, that seems kind of annoying. Now what? Well, I really don't want to have fractions and fractions. So instead of writing this fraction on top divided by x minus 3, I'm going to say that I have the limit as x approaches 3 of 15 minus 5x divided by x. Instead of dividing by x minus 3, we're going to multiply by the reciprocal, 1 over x minus 3. If it makes it easier to see, you can say, oh, we have x minus 3 divided by 1. And when you divide by a fraction, you multiply by its reciprocal, or the flip of it. So yeah, we're flipping it over, multiplying by it. And then we should do some factoring. Here's a place where you can make your life easier or harder. The choice that makes your life harder is the easier choice here. It's easier to factor out 5. If you factor out 5, it leaves you with a 3 minus x. I'd rather factor out negative 5 and be left with a negative 3 plus x. If we factor out negative 5, we're left with a negative 3 plus x, and then we have 1 over x minus 3. But x minus 3 is the same as negative 3 plus x, just written in the opposite order. So those divide to positive 1, and we're left with the limit as x approaches 3 of negative 5 over x, which is negative 5/3. Kind of an interesting point here, just as something that's noteworthy. If, on the other hand, we had factored out just 5, say we had the limit as x approaches 3 of 5 times 3 minus x over x times x minus 3. What's 3 minus x divided by x minus 3? Better question. What's 3 minus 7? What's 7 minus 3? What's negative 4 divided by 4? Negative 1. I could have picked any number there, right? We could have picked 4 or 40,000. 3 minus 40,000 and 40,000 minus 3 are opposites of each other. And when you divide numbers that are opposite signs of each other, but the same value, you get negative 1. 3 minus x and x minus 3, unless x is equal to 3, which is not because it's the limit as x approaches 3. So since x is never 3, 3 minus x and x minus 3 are always going to be opposite numbers that aren't 0, and they're always going to divide to negative 1. So then you could have said this is the limit as x approaches 3 of 5 times negative 1 over x, and then it's still negative 5/3. That's a kind of a useful trick, is that when you see things divided by each other that are opposite, like subtraction, you just get negative 1. Kind of cool. Oh, that reminds me, yeah. Let's do one more of these, actually, because I feel like there's... Oh, sorry.
Got a quick question.
Yes.
In that scenario, could you also just multiply that out and then plug in 3 and get the same answer?
You mean before... I mean after we cancel stuff?
Yeah, so it'd be like, oh wait, no, that still wouldn't.
I think we definitely have to do the factoring here. Question.
Like a number over 0. I thought it'd still be indeterminate.
So 0 over 0 is indeterminate. A non-zero number divided by 0 is something we're going to get to, but it's definitely not indeterminate. It is undefined, which are different things, which I know feel kind of the same. But undefined specifically means does not exist. You won't get a value. It's usually some sort of infinity. Whereas indeterminate means the limit probably actually does exist. You just haven't determined yet what the value is.
What do you do?
Typically not. Not that it couldn't be. So it's definitely possible to have a 0/0 limit whose value ends up being infinity. For example, here's a real kind of silly example, but if I said like the limit as x approaches 3 of, now I have to think. Sorry, one moment. Sure. 2x minus 6 over x minus 3 squared. Let's go ahead and approach 3 from the right, so the limit will actually be something. So we're getting a little ahead of ourselves. That's okay. So here, if you plug in 3, what do you get? 0 on top, 0 on the bottom. So it is a 0/0 type, but it's kind of misleading because really, if you do some factoring, you get 2 times x minus 3 on top, you get x minus 3 times x minus 3 on the bottom. You can cancel an x minus 3 on the top and the bottom, but then you're still left with a problem on the bottom. And now when you plug in that 3, you're getting 2 divided by 0. Or as I would say, so here's what I'm going to say. We don't really have 2 divided by 0. We have 2 divided by a number that's getting very, 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 very close to 0. And is it going to be a little bit positive or a little bit negative in this example? Well, is x a little bit bigger than 3 or a little bit smaller than 3? A little bit bigger than 3. So if you take a number that's a little bit bigger than 3 and subtract 3, we're a little bit positive, right? So my fraction is a positive number on top, a very, 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 very small, but still positive number on the bottom. So whatever the result is going to be positive, because a positive divided by a positive is positive. And then I like to write this little notation here to kind of justify to yourselves, well, it's like we have 2 divided by 1/1,000,000. Right? That's a really, really small positive number. But when you divide by a fraction, what do? You multiply by the reciprocal, which is 1,000,000/1. Oh, that's a really big number. That's 2 million. So if you end up getting a limit where you have a non-zero number divided by something that's getting really, really close to 0, one of 3 things is going to happen. It's either going to be infinity or negative infinity, or if it's double-sided and the sides go different directions, like 1 up to infinity, 1 down to negative infinity, we're going to say it doesn't exist. And your job is to determine whether it's positive or negative, essentially. So here, once I see that it's not 0 divided by 0, the only thing I'm thinking about doing is saying, okay, well, is the whole thing positive or is the whole thing negative? Oh, it's positive because it's a positive divided by a positive. So in this case, we would say that the limit as x approaches 3 from the right of 2 over x minus 3 is positive infinity. So there's kind of a very contrived example of how a 0/0 still could turn out to be infinity. But really, it's just adding an extra layer of stupidity, to be honest. Like I really just took something I knew was going to be not 0 divided by 0 and multiplied it by x minus this over x minus this to make it so it was 0/0 first. So sometimes 0/0 can be infinity or negative. It isn't usually. I will also say, since we're on the topic, if you take the limit as x approaches 3 from the left of 2 over x minus 3, then you would have a 2 on top and a very, very slightly negative number on the bottom, which would mean we would get a positive divided by a negative is going to be negative infinity. Sorry, you can't see that. Apologies. Which in this example would mean the overall two-sided limit doesn't exist because the left-hand side and the right-hand side are going in different directions. Okay, now one more thing, which is going to be kind of an annoying, kind of a tricky question. Does the limit as x approaches 3 from the right of 2 over x minus 3 exist? It's a trick question. Your gut, I feel like your gut says, well, obviously, right? You just said it was infinity. And you're right, we did just say it was infinity, which means the limit doesn't exist. Because for the limit to exist, the function has to be approaching a finite real number, neither of which infinity is. It's certainly not finite. It's also certainly not real. It's not a real number on the number line. It's a number that's off the number line. It's not even a number, really. It's a direction. Just saying we're getting really, really big. So I think I said this last class, or maybe I said it in a different class. I'm gonna say it again either way. When we say this, the limit of something is infinity, we're saying two things at once. We're saying one, the limit doesn't exist. And two, the function also gets really, really big as x approaches 3 from the right-hand side. That's what we're actually saying when we write this notation here. So technically that limit doesn't exist, but we use this notation to be a little bit more specific about the way in which it does not exist. Yeah.
For questions like that are does not exist and positive or negative infinity interchangeable, or do you?
I would say no. I would say even though it is correct to say this limit doesn't exist, we want to give the most correct possible answer, which is to say the limit's infinity, meaning it doesn't exist, and we know the function gets really large. So yeah, I would say they're not interchangeable. Maybe they are when it comes to web work, but typically not. Okay, back to, oh yeah, we still had one or two more 0 over 0. Oh yeah, we gotta do that too. Interesting. Okay, sure. So a couple more 0 over 0 things that come up. Oh, I was gonna do that. Sorry, yeah. So I still want to do one more fraction one because, well, there's something I want you to see. So let's say we had something like numbers here, 12. So we have the limit as x approaches -3 of, sorry, this is when I have to think about what I'm doing here. Sure, let's make it real obvious. 1 over x plus 1/3 over x plus 3. Clearly going to be 0 over 0. So one way to deal with this, which is a little bit more computation, but a little bit less having to think about a special way of doing it, is do what we did before. Get the common denominator. Multiply 1 over x by 3 over 3 and 1 over 3 by x over x. So one way to do this is to say, great, I know I want my common denominator in the numerator to be 3x. So I'm going to have 3 over 3x plus x over 3x divided by x plus 3 over 1 if you like. And then we're going to rewrite this as the limit as x approaches -3. On top, we have 3 plus x divided by 3x. And on the bottom, we would have the same thing, but let's go ahead and multiply by the reciprocal. Say it's 1 over x plus 3. And then the 3 plus x and the x plus 3 are the same. They divide to 1. So we have the limit as x approaches -3 of 1 over 3x, and that's going to be 1 over -9, or -1/9. Or you could try to make your computations slightly less terrible by doing the following. We could say that the limit as x approaches -3 of 1 over x plus 1 over 3 over x plus 3, instead of getting the common denominator in the top here, we're going to multiply both the numerator and the denominator by the common denominator we're looking for, 3x. We still have to identify the common denominator of those fractions. But then look what happens when we do it. So when we multiply the 3x by 1 over x, sorry, don't forget to write the limit. Limit is x equals -3. 3x times 1 over x is what? What is it? What happens to the x's? They cancel, so what are you left with? And what's 3x times 1/3? Right. Over x plus 3 times 3x. It's just a little bit slicker. It's totally not necessary to do it this way, but if you don't like writing more than you absolutely have to, this is a way to write less. D still divide to 1. You get the limit as x approaches -3 of 1 over 3x, which is still 1 over -9 or -1/9. So if you see something like that and you're like, oh, I can just multiply the top and bottom by the common denominator, that will also work out just fine. Okay, sure, let's look at that one. Yeah. So, yeah. So let's say we want to find the limit as x approaches 5 of the absolute value of x minus 5 divided by x minus 5. That's interesting. I never thought about doing it that way. Anyway, sorry. So typically with limits and absolute values, you almost always have to break it down into some one-sided limits because the absolute value function is really a piecewise function. So just as a kind of aside here, the absolute value of x minus 5 is equal to, and this is the way you should always think about question? Okay. The way you should always think about an absolute value is the absolute value of some stuff is equal to that stuff if the stuff is positive. So the absolute value of x minus 5 is equal to x minus 5 if x minus 5 is greater than 0. Or in other words, if x is greater than 5. And if the inside stuff isn't positive, if it's negative, the way you turn a negative thing into a positive thing is by multiplying it by -1. So we say that the absolute value of some stuff, well, if the stuff is negative, it's going to be -1 times that stuff. If the stuff, x minus 5, is negative. Or in other words, if x is less than 5. Sorry, no. Right, too small. So what that means is we're going to have to look at the limit as x approaches 5 from the right side of 5 and the left side of 5 because this function is defined in different ways for each side. So let's look at the right side first. The limit as x approaches 5 from the right of the absolute value of x minus 5 over x minus 5. Well, on the right side of 5, the absolute value of x minus 5 has to be positive, right? You're picking something bigger than 5, you're subtracting 5, it's still positive. So for this one-sided limit, the absolute value of x minus 5 is just x minus 5. And then x minus 5 divided by x minus 5 is 1. So if the limit as x approaches 5 from the right of 1, and the limit as x approaches something of a constant is always just that constant value. It's one of your limit rules or laws. And you can, if you think about this, right, pick any number bigger than 5 in your head. I picked 8. Okay, 8 minus 5 is 3. The absolute value of 3 is still 3. The bottom, 8 minus 5 is 3. Oh, 3 divided by 3 is 1. And whatever number you picked that was bigger than 5, you also got 1. Because any number bigger than 5, this expression is going to equal 1. On the other side of things, the limit as x approaches 5 from the left-hand side. Well, let's think about what's going to happen here. If I pick a number less than 5, like 3, on the bottom, 3 minus 5 is -2. On the top, 3 minus 5 is -2, but the absolute value of -2 is +2. So we're going to get 2 divided by -2, which is -1. But we can also show the math, right? We can actually say, well, we know because of what we wrote over here that the absolute value of x minus 5 is going to be -1 times x minus 5 when x is smaller than 5 or left of 5. So it's going to be the -1 times x minus 5 over x minus 5. And then the x minus 5 gets to cancel, and you have the limit as x approaches 5 from the left of -1, which is -1. And those don't match, meaning this limit does not exist. Graphically, I have enough room here, sure. Graphically, this function looks like this. At 5, it's completely undefined. And then on the right side of 5, it's equal to +1. On the left side of 5, it's equal to -1. So obviously, you can see that as you approach 5 from either side, we don't match up, right? There's no connection there. Yeah, no worries. So let me ask you, let me point this out. So let me ask you a question. Everybody a question. So this is gonna seem a little silly, but what's the absolute value of 6? Just 6, right? Yeah. Okay. What's the absolute value of -6? How do I turn -6 into +6? Right, I multiply it by -1. That's what's happening over here, right? In this case, the x minus 5, oops, you can't see that, sorry. The x minus 5 here is a negative number because since x is less than 5, x minus 5 is entered the realm of negativity. And so to make sure that absolute value of a negative number still spits out something positive, we say, oh, this negative number, x minus 5, we're going to multiply it by -1 to make it positive, and it has to be positive. It's a little weird because it feels like, why are you multiplying it by a negative if you want to be positive? But because it's already negative. And that's very generically also how the absolute value, kind of the straightaway regular, right? The absolute value of x function is defined to be x if x is already positive, and it's -1 times x if x is negative. Or and we put the zero or something, either way. Doesn't matter. That's what's happening here, right? The absolute value of 6 is just x, 6. The absolute value of -6 is -1 times -6. Well, okay, let's see. Sure. Okay, fine. We should talk about that. Yeah. Have you guys talked about the limit as x approaches 0 of sine x over x yet? Okay, doesn't sound like you have. So good. Um, yeah, let's do this one first. So there's a bunch of other stuff. I mean, there's lots more. There's still a lot of things to say about limits, but what I should stop and say is that we've kind of talked about the typical algebraic ways of dealing with 0 over 0 limits. So just as kind of a summary here, when we see a limit, what do we do? Well, the first thing we do is plug in whatever x is approaching. And if you get a number, great. If we get a real number, that usually means we're done. Typically done. But you know what? That's not usually going to happen. Most of the time, when you plug in whatever x is approaching, you're usually going to get a 0 over 0 type. And if that happens, there's three algebraic things we talked about doing. You can try factoring and canceling. And I should say, usually factoring and canceling ends up being part of it at some stage. It's just sometimes before you factor and cancel, you might have to multiply by a conjugate, or you might have to get a common denominator. Wow, can I spell the word common? Maybe. Denominator. And I'll point out for the conjugate, it's good for things like 3 minus the square root of x plus 1, or for things like 1 minus sine of x, or 1 plus cosine of x. Those are all great candidates for to be multiplied by the conjugate of. I could write larger. I see people craning to see what I'm seeing, see what I'm writing. That says 3 minus the square root of x plus 1, or 1 minus sine of x, or 1 plus cosine of x. Those are all great things you would multiply by their conjugates because they come out nice. Um, there's still quite a few other types of limits. There's limits involving infinity, and there's also a couple other weird things. What time? Yeah, okay, so I got like a little less than 20 minutes. So, oh, and I'd say actually we did talk about one other thing which we didn't get too in depth in, but I would say that if you have a right, straighten out. Sorry, it's so crooked. If you have a not 0 over 0 type, then your job typically is to determine the sign, whether it's positive or negative, and then your answer is either positive infinity, negative infinity, or does not exist. Does not exist specifically if it's two-sided and the sides don't match, or opposite infinities. So let's actually continue with that because I feel like I should say more about that because those happen quite a bit. So let's look at another example. Let's say we have, oh, did I lose my numbering? No, cool. 14. Let's say we want to find the limit as x approaches, sure, -6 of 2x over x plus 6 to the second power. So what do I do first? Yeah, I plug it in. If I plug it in, I get negative 12 divided by 0. So what I know about this is I know it's either going to be infinity, negative infinity, or does not exist. But usually, kind of the intermediate steps are I have to do the one-sided limits if it's a two-sided limit. So we need to look at the one-sided limits. So let's first look at the limit as x approaches negative 6 from the right of 2x over x plus 6 squared. It's not, especially with negative numbers, I have to be kind of careful about thinking about what's what here. So the numerator, I don't have to worry about it at all. It's close to 2 times negative 6, which is negative 12. The numerator, you should just actually plug in the value because it's not that important. The denominator, we have a number a little bit bigger than negative 6. I use the number line. Let's see. Negative 6 is right there. So if I'm a little bit bigger, it means I'm to the right. So it's like negative 5.9. This one is not really going to matter because it's squared, but I still am trying to demonstrate the process you would use for anything. So here, I'm thinking, okay, negative 5.9 plus 6 is a little bit positive. So I have a slightly positive number, but then I'm squaring it, so it doesn't matter if it was positive or negative. So the top's negative, the bottom's positive, so the overall sign is positive or negative? Negative. So we get negative infinity. Again, if you feel like that's weird, think about the fact that you're dividing negative 12 divided by 1 over a billion. Oh, that's negative 12 times a billion. That's negative 12 billion. That is super negative. Negative infinity. So and I'll say this a lot as we go on. You've got a fraction. If your denominator is large, the overall value is small because you're dividing not much up into lots of pieces. It's like dividing $5 by 100 people or 1,000 people or a billion people. Everyone's getting fractions of cents. On the other hand, if you have a fraction where the denominator is small, the overall value is large or negatively large, but far away from zero. So in this case, small denominator, large result, negatively large result. Let's see what happens as we approach negative 6 from the other side. As x approaches negative 6 from the left-hand side. So now we're thinking like over here, like negative 6.1. So we have 2x divided by x plus 6 squared. We still get negative 12 on top. Now our negative 6.1 plus 6 is a slightly negative number. So I'm going to write 0 minus with the superscript. But then we're still squaring it. That's not a square. That's a plus. We're still squaring it. So we're getting a negative number divided by a positive number, which overall is negative. So it's still negative infinity. So in this case, since the left-hand limit is negative 6, since the left-hand limit is negative infinity and the right-hand limit is negative infinity, we would say the overall double-sided limit is negative infinity. So we would say that the limit as x approaches negative 6 of 2x over x plus 6 squared is negative infinity. Knowing full well that that means the limit doesn't exist and the function just gets really, really negative no matter which side of negative 6 you approach from. What this really means graphically, and this is very, very standard, when you have limits as x approaches finite numbers that end up being infinity or negative infinity, you have a vertical asymptote. Graphically, and we probably already knew that because you're like, oh yeah, well, of course, if you plug in negative 6 for x, you're dividing by 0, and that gives you a vertical asymptote. So I don't know what the whole graph here looks like, but essentially we can see over here at negative 6, you might want to see what I'm graphing here. I don't know what the entire graph looks like, but I know that whether I'm approaching negative 6 from the left or from the right, the graph is going down, down, down to negative infinity. So it's going to be something like this. Something like this. Oops, let's make that look better. And sure, there's an x-intercept here, so it probably does something like this. But really, I'm just worried about what's happening here. Oh yeah, as x approaches negative 6 from the left, limits negative infinity. As x approaches negative 6 from the right, negative infinity. Cool. If I'm debating whether I want to talk, yeah, let's talk about the squeeze term. So here's a pretty classic example of a limit. The limit as x approaches 0 of x squared times sine of 1 over x. And the problem is sine of 1 over 0 is problematic, right? This inside part, if whether you're approaching 0 from the right or the left, this inside part is kind of blowing up. It's getting very, very large, but sine just does this, right? No matter how big the inputs get, sine is going up and down, up and down, up and down, up and down, up and down. So is cosine. So it's not really getting close to any one number. So then if you multiply it by 0 squared, well, I don't know. Could be anything. Actually, it could be anything, but pretending like it could be. How do you deal with something like this? Well, typically, when we see sine or cosine of some inner argument that's kind of ill-defined, I know it's some inner argument, typically that is blowing up. Think of the squeeze theorem, which I know we haven't said in class. Squeeze theorem or sandwich theorem, whatever you want to call it. Which will state after we do this problem. Why is it useful for sine and cosine? Because sine and cosine have firm boundaries. We know that sine of anything, doesn't matter what's in there, is always less than or equal to 1, bigger than or equal to -1. In this case, sine of 1 over x. In case you're curious, right? If you ever, and again, I know I said this before, I'm saying it again, play with Desmos. It's a great tool. Your instructors probably expect that you're already using it anyway. But if you graph y equal to sine of, take your pick. Plug in literally anything. You can do x. Oh yeah, stuck between -1 and 1. Or 1 over x. Oops, that's not good job. Good job, James. Ah, come on. Fine. We'll never see it. Can't be done. Maybe. Ah, the arrows. Okay, maybe someday we can get there finally. Looks weird, but it's still between -1 and 1. I mean, and really, type anything you like in here. X to the 100th power plus 5x minus 22. I don't know. It looks bizarre, but still between -1 and 1. No matter what, the biggest output sine can ever have is 1. Because the only way you get there is if you do like sine of pi over 2. The smallest output is -1. Slide on. No. Yeah. So in this case, sine of 1 over x is between -1 and 1, between -1 and 1. And then if we're thinking about using the squeeze theorem, our kind of intermediate goal is to make the thing in the middle of this compound inequality look like what we're trying to take the limit of. But we can't just make the middle part what we want to. We have to do the same thing to all the parts. So the way you make sine of 1 over x into x squared times sine of 1 over x is multiply everything by x squared. So we get -1 times x squared less than or equal to x squared times sine of 1 over x less than or equal to 1 times x squared. And then we take the limits of the bounding functions. So we say, oh, the limit as x approaches 0 of -x squared. Well, again, this one we can just plug it in and get -0 squared, which is still 0. Fun fact, 0 is the only number that's its own negative, or stated another way, 0 is the only number that isn't positive or negative. Only real number. Because imaginary numbers don't really have a sense of positivity or negativity, but we're not talking about imaginary numbers. On the other side, the limit as x approaches 0 of x squared is also 0. If the right-hand thing limit, if the thing that's bigger than x squared sine of 1 over x is limit to 0, and the thing that's smaller than x squared sine of 1 over x also has a limit that's equal to 0, then the middle thing is less than or equal to 0 and bigger than or equal to 0. It's got to be 0. There's no other value that's left. So we can say by the squeeze theorem, or sandwich theorem, whatever you want to call it, the limit as x approaches 0 of x squared times sine of 1 over x is equal to 0. Sorry, I'm getting off the page here. Apologies. Graphically, you can really see this. So if we look back at Desmos for a moment here, check this out. So if we graph x squared and negative x squared, and then we graph x squared times sine of 1 over x, and we zoom in a bit, you can kind of see, oh, look, that sine function is stuck between positive x squared and negative x squared. And as we move closer and closer and closer to 0 for x, the y values are just bouncing back and forth, back and forth, back and forth, back and forth, but still getting closer and closer to 0 because there's nowhere else for them to go. So you're squeezed between these two functions that are squeezing you down to 0. So you have to be 0, even though you're like, oh, I think like that. It's kind of neat, I think. I think it's really neat, actually. Squeeze theorem is pretty useful. Where else was I going to go here? There was something else. Oh, yeah. Yeah, okay. So, sorry, I just want to make sure I'm saying all the things I want to say. So much time, sure. Oh, I know what I should ask you all. So, have any of your instructors started talking about the precise definition of a limit, also known as a delta epsilon proof? Okay, well, let me know if they do, because we definitely will talk about it if we need to, but I don't want to burden you with that task if it's something you don't have to see. It usually is part of the content of 21A, but sometimes people skip it, and if they skip it, it's not like you really use it again later, unless you are a math major. But if you're not a math major, you probably never will see it or need it again. So let me see. So one thing we'll start talking about and continue next time is now kind of the limits that end up having limits to infinity. For example, if I wanted to find, I think I lost my numbers here. Not there. So if I was going to try to find, say, like the limit as x approaches infinity of 2x squared plus 3x minus 5 divided by 5x squared plus 6x plus 1, excuse me, this is what we call an infinity over infinity type of limit, right? The numerator is getting infinitely large. So is the denominator. What's infinity divided by infinity? Anything you want it to be. So very, very much like 0 divided by 0 is an indeterminate form, infinity divided by infinity is also an indeterminate form. Meaning when you encounter a limit like this, you have more work to do. And the answer could be any real number, or it could be infinity or negative infinity. Just like with the 0 over 0 limits, right? Those answers could also be any real number, but or infinity or negative infinity. So what's kind of the process for dealing with this? Well, you might already know what the answer to this is because you maybe seen something like this before. The process for dealing with a limit like this is typically either to factor out or divide out, listen to these words, the largest power of x in the denominator. Here they're the same. I'm going to divide everything by x squared or factor out x squared. But if the largest power happens to be in the numerator, you want to pick the largest power in the denominator. We'll probably see that next time. But here, you could either do this by writing it as the limit as x goes to infinity of 2x squared divided by x squared plus 3x divided by x squared minus 5 divided by x squared divided by 5x squared divided by x squared plus 6x divided by x squared plus 1 divided by x squared. What I've really done here is I've multiplied the top and bottom by the same thing, 1 over x squared, and distribute it and then rid of its fractions. And then we simplify. We write it as the limit as x goes to infinity of 2x squared over x squared is 2. 3x over x squared reduces to 3 over x. Negative 5 over x squared is what it is. Similarly, on the bottom, you have 5 plus 6 over x plus 1 over x squared. Now, as x gets really, really large, what happens to 3 divided by a really large number? Is it big or is it small? Very small. How small? Like really close to zero. And that's true for the rest of these. 5 divided by x squared, also very small. 6 divided by x, also very small. 1 divided by x squared, also extremely small. So in the end, we end up getting 2 plus 0 minus 0 over 5 plus 0 plus 0, which is 2/5. Typically, we see that when you have a limit to infinity, if it's a rational function over here, and the leading coefficient, the degree on top and the degree on the bottom are the same highest power of x, the limit ends up being the fraction or quotient of the leading coefficients. So just for one more example here, if I asked you what the limit as x approaches negative infinity of 5x plus 2x cubed over x squared plus 5x plus 7x cubed was, you could say without doing, whoops, you'd like to see it, without doing any work, what should the limit be equal to? I've written it kind of terribly, but what's the degree on top? Yeah, the answer is 2/7. Because if you wrote this in the normal way, you write it as 2x cubed plus 5x over 7x cubed plus x squared plus 5x. But you don't have to write it in the normal way to see what the biggest terms are. So on top, here's my leading coefficient, even though it's not written in front. The leading coefficient is just the coefficient of the highest power. On the bottom, there's my leading coefficient. And since the degrees are the same, right, they have the same highest power, that's going to be 2 over 7. If you're asked to show work, which you probably will be, you can either do what we did before and divide everything by x cubed, or you can decide to factor out x cubed if that feels nicer to you. You can write it as x cubed times 5 over x squared plus 2 over x cubed times 1 over x plus 5 over x squared plus 7. The x cubes divide to 1, and then just like last time, 5 divided by x squared is going to be small, 1 over x is going to be small, 5 over x squared is going to be small. So we're left with 2 divided by 7. I prefer probably doing it this first way, but doing it the second way it's really the same work. It's just a different way of writing it. All right, that is all the time I have for today. See you all on Thursday. Well, we'll probably talk more about limits. And do let me know if either of your instructors starts talking about delta epsilon proofs and the precise definition of a limit. And I'll be over in El Centro for office hours in a few minutes.